So, now you can see that I can recast this definition of the density of states into more usable representation. So, what I am going to do here is rewrite this density of states as you can take S the spin of electrons to be half, and that will make the 2s plus 1 as 2. So, I can write density of states as V into 2m by h cut square raised to 3 half, and divided by 2 pi square into e raised to 1 half, okay, because there is a m by h cut square also, which I have taken inside the square root. So, it has become raised to 3 half. Okay. So, and here also I can write down the free energy, the Fermi energy as so I am going to just write it somewhat closer, and writing down the Fermi energy as h cut square by 2m into 6 pi square. 6 pi square will simply become 3 pi square, because 2s plus 1 is 3. So, let us use that, and this becomes just 3 pi square into n by v whole to the power 2 by 3. Alright, so it looks like more usable to me at least. And one more trick here, we can substitute for what we will do is from the energy Fermi energy expression, I can write for 2m by h cut square as 1 upon EF into 3 pi square n by v to the power 2/3, and if I raise this to the power 3 by 2, then I can say that this is nothing but 1 upon Fermi energy raised to 3 by 2 into 3 pi square n by v. Now, you can simply plug this value of 2m by h cut square raised to 3 by 2 here in the density of states. So, let us call the density of states expression as equation 3, and let us call this as equation 4, and substituting 4 in 3 gives us, I can write down my density of states as V upon 2 pi square and into 1 upon EF to the power 3 half into 3 pi square n by V into e raised to half. So, you can see a lot of terms can be knocked off. You can knock off the 2 volumes, you can knock off the pi square, and what you have at the end of the day is just 3 by 2 n over EF to the power 3 half into square root of E. And I think this is a more convenient use expression for the density of states. Okay. Right. So, you can easily say this is the right expression, because if I integrate this rho e over the entire you know um, at t equal to 0, if I integrate this density of states, I will just get n. So, it is very easy, you can just check. This will give me nothing but 3 by 2 into n upon E f to the power 3 by 2, and when square root of E is integrated, it gives you e raised to 3 by 2 into 2 by 3. So, this is nothing but n. So, my expression of the density of states is correct. Okay. Fine. So, now I have my density of states. I am going to compute some very important quantities, thermodynamic quantities. So, this is a very important expression for me. Okay. So, the first important quantity that I am going to in fact, the two quantities that we are going to be computing are, we know that in the limit n tending to infinity and v tending to infinity, which is the thermodynamic limit, I am going to be computing the an expression for chemical potential, but for that I will start with the expression for n. Now, n is nothing but integrating 0 to infinity the density of states. Now, I know this is the energy density of states into my Fermi function dE. Let us understand the integrand and the limits here. This is not just arbitrary integral, it has a direct consequence from summing over discrete degrees of discrete energy of states and discrete states of energy. And what I have done is that, if you recall, we had simply this summation over all occupation numbers or summation over all the Fermi functions. So, my integral has become basically this, my summation has basically become an integral, which is overall density of states, and whatever function that I wanted to compute, okay, that is my summation over j f e j will simply become integral rho e f e d e. Now, if I am at t equal to 0, then I know that all energy levels above the Fermi level will be not occupied, will be vacant. So, this Fermi function is basically 0 above the Fermi energy. So, for the purpose of integration, the upper limit will be just the Fermi energy if you are doing the integration at t equal to 0. But if you allow the temperature to become non-zero, then in principle there is no upper limit on the energy, because it can go to infinite. Of course, the probability density of finding a state of infinite energy occupied will be 0, but the mathematical upper limit of the integral will be not Fermi energy anymore, it will be infinity at non-zero temperatures. Okay. So, do not worry about infinity, the Fermi function will take care of it. Okay. So, since we are going to be interested in temperatures that are non-zero, so I am going to write it as thermodynamic limit and non-zero temperatures. I am going to be interested in integrals of this type for total particles and for total energy, we will write down the integral as our density of states into energy into Fermi function integrated over all possible values of energy. In this case, the energies will go from 0 to infinity. Okay. Now, if you look at these two integrals, both these integrals for E and N, let us give them some numbers, equation 6 and equation 7, both 6 and 7 are of the type, they are of the type an integral 0 to infinity some function phi of E into f of E dE. For example, for in equation 6 we have taken the function phi as nothing but the density of states, okay. And in 7 we have taken the function phi as E times the density of states. So, both the 6 and 7 are of this type, okay. So, I am going to call this integral as integral I, okay. And we can write down, we can compute, before we do that, let us observe a few things about this function phi. We know that the function phi is a function of energy. So, phi is a function, and I am going to say it is a function that is smooth, okay, and which means it can be written as a derivative of some function. So, I can write down phi as a derivative of some function. Okay. So, in this way I can write down the function psi as an integral of this function phi of E, okay. So, if you look at this this is just by the fundamental theorem of calculus, okay. So, so now I can do the following. I can compute phi, compute the integral I. So, I can write down integral I as 0 to infinity I am going to write down the Fermi function first and then write the function phi of E. So, if you do it by parts, then it becomes simply the Fermi function into integration of phi, which is nothing but my function psi, okay, and the limits here are 0 to infinity minus integration of the derivative of the Fermi function into psi. Please note that our integration of phi has already been taken to be psi. That is why Okay. Fine. So, then I can simply write down just this is enough to write down. Okay. Now, this will be a function of E prime. So, that is what I have done, and you can see that the first term here goes to 0, simply because at infinity we do not know what is going on with the function psi, but I know for sure that my Fermi function is 0 at infinity. So, this is 0 at infinity, and at 0 the Fermi function is finite, but psi of 0 is 0. Okay. And that is very clean, very easy to see from the fundamental theorem of calculus that I have written here. The way I have defined psi, its value at epsilon equal to 0 is nothing but the integral phi, where the definite integral has the same upper and lower limit. So, then psi of epsilon at epsilon equal to 0 is 0. Okay. So, that pushes the first term to 0, leaving me with the second term alone, which is negative integral of f prime psi e dE. Okay. So, now we can our left hand side is basically the integral 0 to infinity f e phi e dE. So, let us call this as some equation which is equation number 8. Couple of things to note here. First of all, the behavior of our f prime. I want to solve this integral. This integral can be solved for a general class of the functions phi, provided we use the fact that our f prime is very sharply behaving. You see, the Fermi function at t equal to 0. So, my t equal to 0, this chemical potential becomes EF, and this is sharply falling to 0, and it is 1 everywhere as a function of E. Okay. So, at E equals to EF, then I know my Fermi function falls to 0, but at all non-zero temperatures I know that my Fermi function allows for some excitation of electrons above the Fermi surface. So, a small fraction of electrons of the order T by Tf are excited above the so, I am going to say that this is my excitation . Okay. So, these are precisely the particles that are excited. And this would be at some energy scale which is mu. This is not exactly at the Fermi energy, because this scale has moved slightly with temperature, but I know it is about that is the chemical potential for my problem. So, I know for sure that if I take the derivative of Fermi energy, then it will be very sharply peaked around this mu, and particularly I will take the negative derivative of the Fermi function. Then I know for all these values where Fermi function is constant, there shall be no derivative or no variation, and very close to mu I will have a derivative non-zero peaking at exactly at mu, and again because it has to come down to 0 as the Fermi function becomes 0 and remains 0 all the way to infinity. So, this derivative has to come to 0, and you can see this is a sharply peaked function where the width is of the order of twice kT. About kT over k times Tf is the fraction of electrons excited above the Fermi surface. So, the width of this is somewhat twice kT, and now using this fact and the fact that function phi of E is smooth around my energy E equals to mu, okay, I can expand psi of E in powers of the displacement around mu, okay. So, I can expand it in powers of E minus mu. So, I can write down psi of E as summation over, it is like a Taylor series. So, summation m going from 0 to infinity 1 upon m factorial, just a Taylor expansion of psi around equals to mu. You can write down E minus mu to the power m into del psi by del E, the mth derivative at E equals to mu. This is the Taylor expansion. Now, you can plug this so called smooth behavior of psi in equation 8 and try to solve it. This is the last step that is required, and the smoothness of psi helps us to solve the equation 8. So, you can see that plugging 9 in equation 8 gives us integral that we are chasing 0 to infinity f of E into phi of E as negative of the integral 0 to infinity f prime E into summation m going from 0 to infinity 1 upon m prime m factorial E minus mu to the power m, and since psi is just a function of E, I am going to write down the partial derivative as the ordinary derivative. Psi is not a function of any other variable. So, purely respecting that, I am going to write it as mth ordinary derivative of psi at E equals to mu. And at this point I would like to remind here, this mu is the chemical potential. The distinction of chemical potential from Fermi energy is only at non-zero temperatures. Like I have already showed, E is our energy that can take values between 0 to infinity. Mu is our chemical potential which sets the scale of the energy in some sense. So, at t equal to 0, the chemical potential becomes the Fermi surface energy or the value of the Fermi energy. So, the scale of the problem, which is mu, becomes the Fermi energy at t equal to 0. that is the only distinction. So, at any non-zero temperatures the scale remains the chemical potential as reflected in our Fermi-Dirac statistics. If you go back, as you can see here, this is the scale of the energy, okay, which is the chemical potential. Now, let us get down to what we were evaluating, right. So, now you can see that there are a couple of things I can do with my integral. I can take out the terms which do not depend on epsilon outside the integral, and in doing so I can take out the entire summation. So, I can write down negative summation of m going from 0 to infinity 1 upon m factorial, and I can also take out the mth derivative of psi with respect to epsilon, because keep in mind that the mth derivative of psi, that is a function of epsilon, at e equals to mu is independent of E, okay. This derivative is independent of E, and what I am left over with is just the now the integral 0 to infinity f prime E into, let us move all this description on the right hand side, because I need some space here, yeah, f prime E into E minus mu to the power m dE. Okay, I think I am not missing any terms here, fine. So, now let us try to solve this by some substitution. Well, I can easily make two substitutions here. The first is I can substitute for the Fermi function. So, substituting for the Fermi function, which is basically my the Fermi-Dirac statistics 1 over e raised to beta my energy minus the energy scale, the chemical potential, plus 1, okay, our FD statistics. If I take this and perform a first derivative, so the first derivative with respect to epsilon would simply be would simply give me e to the power beta E minus mu into beta divided by e to the power beta E minus mu plus 1, the entire thing squared. Okay. And the entire thing has to be taken with a negative sign, because that is what comes when you square the denominator. Fine. So, if you plug this in the previous expression, you will get the integral 0 to infinity f e into the function phi e dE, as there is already a negative sign that becomes positive now, with the summation m going from 0 to infinity 1 upon m factorial dm by d epsilon factor of psi at e equals to mu into an integral 0 to infinity, and what we have here is f prime, which is nothing but beta e raised to beta E minus mu over e raised to beta e minus mu plus 1 whole square, and have beta, I got an e minus mu raised to the m into dE, fine, right. So, now just make a small substitution to solve this integral. For e minus mu into beta as some x. So, we can write down for beta times d epsilon as dx. So, that will make my integral very simple in terms of x. So, I can write down my integral as and I can write down this integral as so limits will well, the lower limit when epsilon goes to 0 becomes minus mu beta. Okay. So, the lower limit will transform to minus mu beta because of the substitution I have made, and when epsilon goes to infinity, the upper limit remains infinity, and with the substitution e minus mu into beta, my integral becomes e to the power x into x to the power m into beta to the power minus m into dx over e raised to x plus 1 the whole square, fine. So, since beta is a function that is independent of x, I am going to write down this outside, okay, and remove it from here. It is only a function of m. Okay. So, now we can solve this integral. Let us put a label on it. We are at 9. So, let us put the label 10. So, I am going to solve this integral at very low temperatures. Now, but low temperatures means what? I need a scale. At the beginning of the discussion I said low temperature, but at that time if I had introduced to a temperature scale, it would have been meaningless because I have not discussed the problem in general. But now I have a temperature scale here which is mu. So, I can say that at very low temperatures means my beta times mu should go to infinity. Okay. So, mu over kT should go to infinity, that is the meaning of low temperature. So, I have an energy scale which is mu, now makes sense, and that means my minus beta mu will be minus infinity, that is the meaning of low temperature, okay, right, because low temperature means T going to 0 or beta going to infinity. You can also say absolutely low temperature, okay, but here I have given a scale argument. In any case they both imply the same. This is more beautiful in the sense that you do not have to take the absolute limit that T goes to 0 or beta goes to 0. You can say that okay at finite T, but as long as mu times beta goes to infinity, I will take this as a low temperature limit, fine. That is a more intuitive way of saying low temperature, that you compare two scales, okay. So, now in this low temperature limit my integral becomes the summation m going from 0 to infinity beta to the power minus m over factorial m d raised to m over d e to the power m. Please do not be bogged down by this nasty expression. This is a very straightforward calculation which we are simplifying in very straightforward steps. There are no very absurd mathematical formulations. It is a straightforward thing, and every step will be explained in detail. In fact, the integral that I am going to run into very soon will also be explained in the mathematical prerequisites, which is discussed as a separate lecture, so that I do not take a long digression into the problem. So, then this integral at the low temperature will have now new limits going from minus infinity to plus infinity, e to the power x x raised to m over e to the power x plus 1 a whole square dx. Now, it seems that we have to just solve this small integral to compute our answer. Yes, but it is not a straightforward integral. Okay. So, let me call this as equation 11. So, this integral minus infinity to plus infinity can be solved for certain types of m. First of all, this integral is 0 for values of m which are odd. Look at the interval of the integral, it is from minus infinity to plus infinity. Okay. So, if the integrand here is odd, then the integral is 0. Now, the integrand here, which is this function, can be seen as a I can write it as minus infinity to plus infinity. I can rewrite e raised to x upon e raised to x plus 1 the whole square as simply multiplying both the numerator and denominator with e raised to minus x. This simply becomes just rewriting it. Okay. Now, you can see that why the evenness or oddness of this integral depends entirely on the value of m. Okay. So, I can say that this is 0 if m is odd, okay. Or you can just say that since these are the two same integrals, this is the answer to this is nothing but. Okay. So, it just we just have to compute for values of m which are even now. So, the integral exists only for m equals to 0, 2, 4 etc. So, let us take two values and stop there. The reason being higher orders of m will be basically proportional to higher powers of kT. For example, m equal to 4 will give you a term that is proportional to kT to the power 4, and if we are since we are doing everything at low temperatures, higher orders of temperature would be would be vanishing in nature. So, we will stop at the first two orders. So, let us take for m equal to 0 and 2. Okay. So, for m equal to 0, my integral will simply become minus infinity to plus infinity x square, sorry, this simply becomes e raised to x over e raised to x plus 1 the whole square dx. Okay. And this can be solved by simply substitution of you know e raised to x plus 1 as some variable t. Okay. So, you take it square it up and the numerator would just be just dt. Okay. Now, what about the limits? Limits have to be, you have to be careful. I am substituting e raised to x plus 1 as t, which means the x going to minus infinity limit will transform to t equal to 1 and the x going to infinity will transform to t equal to infinity. So, this integral would now be, can be straightforwardly computed. It is a minus of 1 upon t, and between the limits 1 to infinity this would simply be 1. So, now you can go back here and say that for m equal to 0 I have 1. Let us compute for one more value for m equal to 2. So, for m equal to 2 this integral will give me minus infinity to plus infinity e raised to x into x square upon e raised to x plus 1 dx, and this integral can be shown to be pi square by 90. I leave that as an exercise and we will do this in the separate tutorial. Or you can take it up as a personal homework problem, but I am going to say that you follow up the math prerequisites. We will discuss this integral there. So, let me just confirm the value of this integral, that it is indeed pi square, no, it is pi square by 3, I am sorry, it is pi square by 3. Okay. So, either you can do it yourself or you can refer to the math prerequisites and we will show it how to get this integral there. So, now with the two values of m 0 and 2 we plug these values in our final expression, which is equation number 11. Okay. So, I will say that plugging for m equals to 0 and 2 in equation 11, we get the final answer as integral 0 to infinity as the first term would be just m equal to 0. So, that would just give me psi at equal to 0 okay, plus m equal to 2 would give me kT square by factorial 2 into our pi square by 3 into the second derivative with respect to e of the function psi at e equals to mu. Okay. So, I think that is it. Yeah, that is it. And since I have not gone to m equal to 4, I will say that I have dropped terms of the order k b t to the power 4. Okay. So, that would have been the prefactor of m equal to 4. We are not going to the 4th order, because anyway this is a theory at low temperatures. So, we will stop at the quadratic term in temperature. Now, what is this the function psi of epsilon? This is nothing but the way we have defined psi upstairs. Psi is nothing but the integral of function phi. If you look here, the function psi here is nothing but the integral of our function phi, which is on the left hand side. Okay. So, I am just going to write down this. It is an integral over phi okay, but this is integral, and then it is for our function psi computed at e equals to mu. So, what I am going to write down is that this is an integral going from E 0 to mu, okay. That is the value of function psi at mu. All right. So, the second term would be nothing but k b t square, okay, and I can write the prefactor here as pi square by 6, and this is d square psi by d e square. So, psi itself is so I can write this as just d phi by d e, okay. Okay, because our function psi is just integral okay. So, you can take this as when you take the derivative of double derivative of psi, you will get it is equivalent to taking a single derivative of phi. Okay. So, then you can say that if this is for the integral okay. So, if you can call this as integral 12, and now you can take some cases. For example, you can solve for some thermodynamic properties. So, now we are in a position to compute n and in fact, I can say n and e. Okay. So, let us see what we get if we try to compute n. So, for n I have to take my function phi of e as just the density of states, okay, because if you see the left hand side, okay, n would be nothing but integral E going from 0 to infinity f of E into density of states dE. So, putting phi as rho E, this will give me the n, which means on the right hand side I have to put phi as rho E. So, if you do that, what you get integral E going from 0 to mu rho of E dE plus kBT the whole square into pi square by 6 into d by dE of rho E at E equals to mu. Now, we know what is the formula for the density of states. So, the formula for density of states we are just going to copy it from upstairs. The density of states here has a neat formula here. Okay. So, let us just copy paste this formula. So, since this is the density of states, okay, so what I am going to do is just plug this value in the previous equation, and this will give me the left hand side is n, and if you look at the right hand side, I can take a couple of constant prefactors outside into integral of square root of E, that will give me nothing but e raised to 3 by 2, but in the limits mu and 0 this will simply become mu into 2 by 3, fine, plus I will have a kT square into pi square by 6, and if I take the derivative I will again get all the same prefactors, and the derivative of square root of E is nothing but 1 by 2 into e raised to minus 1 by 2, but at equals to mu this will be just mu raised to minus 1 by 2. Okay, so now you are easily seeing a lot of common prefactors that you can probably cancel. So, what you can do straight away here is the following: you can knock off these n's from all the sides, and what you can also do is now basically take so your right hand side becomes 1, you can take 3 by 2 E f to the power 3 by 2 outside. Okay. So, what you will be left with is basically 2 by 3 in fact you can do one more thing, you can knock off this this also, and simply take 1 upon the Fermi energy to the power 3 by 2 common, and what you will be left is basically mu to the power 3 by 2 plus kBT square into pi square by 8 into mu raised to minus 2 1 by 2 Okay. So, now you can use this to derive an expression for mu as a function of T. So, we have this equation here which can be used to compute how the chemical potential varies with temperature. So, I have said for one value of temperature that the chemical potential becomes the Fermi energy, but what happens to the chemical potential as you vary the temperature? This is something that we would like to know. Okay. So, that can be computed very easily. You can multiply both sides with e to the power Fermi energy to the power 3 half. So, what you get is basically just the equation, the expression in the brackets, and from that also if you take out mu raised to 3 half outside, what you get is just 1 plus kBT the whole square into pi square by 8 into mu raised to minus 2. Okay. So, now what you can do here is the following: you can invert this expression for mu. So, you can say that this is but before that you can raise the entire equation to power 2/3, that would become make it EF is equal to mu into 1 plus kBT the whole square into pi square by 8 mu to the power minus 2 raised to 2/3. You raise the entire equation to the power 2/3 and simply transpose to the opposite side. So, mu becomes EF into 1 plus kBT the whole square into pi square by 8 into mu raised to minus 2 raised to minus 2 by 3. So, you can write down this as you can write this entire thing as pi square by 8 into kBT over mu the whole square raised to minus 2 by 3. Now, since we are in the low temperature approximation, for low temperatures, meaning my temperatures are much smaller than the scale mu. So, I have a scale here. So, such that this ratio becomes much smaller than 1, I can expand this term in powers, and to lowest order I can write it as e to the power the chemical potential as EF into 1 minus 2 pi square. Okay. So, I can write it as just pi square by 12 to make things simpler, into this dimensionless number kT over mu the whole square. Now, you can look, now this is how basically this tells us how mu varies with temperature. Okay. So, I will say that this equation tells me how mu varies with temperature. Okay. So, for that to tell me for that to basically be valid, you can see that my equation requires the left hand side in the right hand side to be computed. Okay. So, this requires basically so how do I circumvent this problem? I am going to find out mu, but that requires me to compute mu for the right hand side. So, we can at least in the series in the sense that when mu is very close to the Fermi energy, then to lowest order we can tell how mu will vary. Okay. So, at very low temperatures, again the idea is that my temperature is very close to 0 tending to 0, I can say that my mu is nothing but the Fermi energy only on the right hand side. Okay. So, then I can write down my chemical potential as mu that goes as EF minus pi square by 12 into kBT over EF. This is like saying that if I was at 0 temperature, then how would the right hand side behave? So, the right hand side would behave like that. As T goes to 0, the right hand side would behave like this. It is not exactly 0, because exact 0 is when mu becomes Tf. So, this is how typically one expects the chemical potential to behave with respect to temperature. So, if I plot the chemical potential over the value at t equal to 0 as a function of T over Tf, okay, because I can take my kBT over Ef as T over Tf. Then I can start from 1, because that is what the equation would predict at t equal to 0, okay, and eventually somewhere along the lines where this is of the order of 1, you would be hitting the 0 of the chemical potential, and from that point onwards your chemical potential will turn negative. So, this is the area of negative chemical potential. But you already know that this is a temperature which is very high, only of temperatures comparable to Fermi temperatures your chemical potential turns negative. So, you need to really climb up in temperatures that much for the chemical potential to turn negative. Another quantity that we can quickly compute is the total energy. And that is the quantity that will tell us how heat capacity behaves at low temperature due to these Fermi electrons. Okay. So, the missing component of the overall heat capacity, that is due to Fermi electrons, will now be addressed. So, we are now at the final leg of our discussion. So, the energy, as we know, is given by an integral 0 to infinity of E times the density of states into the Fermi function. This is what we know in the continuum limit, okay, in the thermodynamic limit. That we already know. Our sum has become an integral, the density of states is rho e, and this is our Fermi function, and that is the value of energy. Okay. So, the total energy is nothing but this integral. Now, we already know an integral of this sort. So, here I have a formula So, if you look at equation 12, in the left hand side, if I replace phi of E as E times the density of states, then it is nothing but the expression for total energy. In the right hand side, I simply plug phi as rho times E. Okay. So, what I am going to do is basically plug phi as rho into E. Okay. So, I am going to just plug phi as rho E into E in equation I believe 12. Yeah. So, what I get is the left hand side is the energy, so this would be 0 to infinity, because we are at finite temperature, all energies are possible now. Energy times the density of states into the Fermi function, and the right hand side was nothing but integral 0 to mu rho E times E dE. So, this was our function phi of E, okay, plus pi square by 6 if I am not wrong, yeah, pi square by 6 into kT square into d phi by dE. Into d phi by dE. Now, my phi is again, as I said, rho E into E at E equals to mu. So, this is nothing but my phi of E. Okay. But I already know that my rho of E, the density of states, which was written here, yeah, this expression. Okay. So, you can I know the density of states is this. So, I can compute what is my the integral. So, it is very simple now, because I can write down this integral as keep all the constants outside. So, my energy E would be nothing but I can take 3 by 2 into n over E f to the power 3 half, and I believe the same will come out from the second term also. So, I am going to keep it outside the big bracket, and this would be an integral of e raised to 3 by 2, because there is already an E outside. So, E times rho would be e raised to 3 by 2. So, that will be nothing but e to the power 5 by 2 into 2 by 5, and the limits would be 0 to mu plus pi square by 6 into kBT the whole square, and again I have taken all the constants outside. So, I will be taking derivative of e raised to 3 by 2. So, that would be 3 by 2 into e raised to half at E equals to mu. Fine. So, now you can see that this becomes a nice expression. So, I can write it as 2 by 5 mu to the power 5 by 2 plus pi square by 4 kBT the whole square into mu to the power half. Okay. Right. So, what you are now looking at is an expression of the internal energy of the Fermi gas as a function of temperature. So, one final hurdle before we derive the expression for heat capacity is to simplify this expression. So, what I am going to do now is just rearrange the terms a little bit here. So, what I will do is I will pull out a factor of 2 by 5 also from the bracket, and that will make the prefactor outside as 3 by 5 into n to the power so please cut it. Tell him. Right. So, what we can do here with this expression is to rearrange the terms a little bit here, and I can pull out a factor of 2 by 5, that will make it 3 by 5 inside sorry outside, and this will be E in the denominator, e to the power 3 by 2 Fermi energy to the power 3 by 2, and what I will have inside is mu to the power 5 by 2 plus 5 pi square by 8. Okay. So, this is multiplied to kT square into mu raised to half. Now, what I can do now is just take mu non dimensionalize this mu by simply saying that I am going to keep a factor of Fermi energy outside, and what I will do is take Fermi energy inside to the power 3 half. So, that becomes mu over E f to the power 5 by 2, and I will do the second term as I just want to start from the beginning. I am not getting the right words, right. So, what I can do now is basically simplify this expression by pulling out a few factors. So, I am going to pull out a factor of 2 by 5, that makes my prefactor outside as 3 by 5 into, I am going to write down this as n times the Fermi energy, and I will write the first term inside the bracket as mu over the Fermi energy to the power 5 halves, okay. And the second term inside the bracket I am going to write it as 5 pi square by 8 okay, because I pulled out a factor of 2 by 5. Okay, into kT over the Fermi energy to the power 2, and the last term I am going to write as mu over Fermi energy to the power 1/2. Okay. So, I can see the terms inside the parenthesis have become dimensionless. Each energy scale is divided by another energy scale. What has happened is that outside the parenthesis now the energy scale has come, that is free energy, that is the Fermi energy, which sets the scale for my total energy. Okay. So then I can now utilize I can say that this is my expression for energy. This can be simplified further. Using my already derived expression for the chemical potential. So, I am going to use this definition of the chemical potential. Okay. So, this nice definition of the chemical potential comes to our use. So, you can see that I can write mu over EF as 1 minus pi square by 12 into kT upon F EF raised to 2. Okay. So, I can write down my energy as E equals to 3 by 5 into n times the Fermi energy. This was the prefactor outside. Mu over EF to the power 5/2 is just 1 minus pi square by 12 into kT over Fermi energy to the power 2 raised to 5/2. Now, in the limit of small temperatures, when kT over EF is very small, I can expand this power to just linear orders and say that this is nothing but 5 by 2 into kT square over EF square. Okay. And the second term is 5 pi square by 8, if you look here, into kT square over EF square, and then it is multiplied to mu over EF to the power 2, which again I can just to linear order write as 1 minus pi square by 24 into kT over EF the whole square. Okay. So, what have we done here? We have made some simple approximations. So, whatever we have done here is basically we have used the fact that kT over EF is a number that is much smaller than 1, and to linear order the fractional power of 1 minus pi square by 12 into kT by EF square simply reduces to the approximations that we have taken. So, I am going to write down just one of them, that 1 minus pi square by 12 into kT over EF the whole square raised to the power n is simply 1 minus pi square into n over 12 into kT by EF to the power 2. That is the approximation I have used. Okay. So, let us see what finally I have. Now, easily you can see, since we are in the approximation kT over F much smaller than 1, I am going to drop terms that are higher than quadratic in nature. So, dropping definitely the 4th order term. Okay, I am going to drop this term in comparison to the quadratic term, my expression reduces further and I get the expression for the energy as 3 by 5 n times EF into just the two terms which are quadratic in temperature, and you can see it is basically 5 by 8 minus 5 by 24 which I have to do. So, that would be just 1 plus 5, I am going to write it as 5 pi square by 8 into kBT over EF the whole square into 1 minus 1 by 3, okay. And this is nothing but I can write it as 2 by 3, and so this is nothing but 5 by 12, okay. Just the simplifications that I have used here. So, now you can see that the leading term as T goes to 0, that is at absolute 0 temperature, the energy of my system is not 0. In fact, it is given as the energy of my Fermi electron gas at absolute 0 is not 0, it is given as 3 over 5 n times EF, okay. But this is not a thermal energy, this energy is not thermal in the sense that at T equal to 0, if I touch a metal which has these electrons having a total internal energy of 3 by 5 n times EF, and EF is of the order of 1 electron volt, it is a very high amount of energy, I still feel as cold as as cold as hell, because there is absolutely no room for electrons to conduct. At T equal to 0, the electrons have occupied all the energy levels up to the Fermi level, and hence in spite of the fact that this energy is very large, these electrons cannot conduct heat to my palm or my hand which is touching them, and so I feel nothing but very cold as T tends to 0. This energy is not thermal in nature, it cannot give rise to any conduction, and this energy purely is a consequence of the Pauli's exclusion principle that drives electrons to sit at different energy levels in a quantum system, okay. So, at temperatures that are non-zero, okay, I can write down my energy with this expression, let us call this as the final result, and I know that the heat capacity, which is Cv, the heat capacity at constant volume, is given as the derivative, temperature derivative of the total energy. So, if I use the above expression that I have derived for energy, then the first term, the Fermi energy component provides no component, and it is clear why it provides no component to the heat capacity, because it is not thermal in origin. The second component provides a contribution, and that is 3 by 5 NEF constant prefactor into 5 by 12 pi square kb square over EF square and 2 times T, and you can already knock off a lot of terms here. So, you can knock off this and you can knock off 1 EF, and this becomes 6 and that becomes just 2. So, what you have in the end is just pi square by 2 into n times kb square T over EF. Okay. It should have the units of n times kb, heat capacity is natural units, okay, because kT is energy scale. Now, I can do something with this. I can say that my Fermi energy is in order to express in terms of a temperature scale, I am going to write down this as kbTF. So, my heat capacity is now due to thermal energy is pi square by 2 into n times kb into T over Tf, and I am going to rearrange this basically in some way. I am going to write it as pi square by 2 into n into T by Tf, the entire thing times T. Yeah, entire thing times kb. Okay. So, this factor here is an extensive factor. So, I can call my Cv now as pi square by 2 into some n prime into kb, and I am going to call this n prime here as the number of electrons that contribute to heat capacity, okay, because heat capacity is an extensive quantity, and this number smoothly tends to the total number of particles as the temperature becomes much higher and becomes the Fermi temperature. If you see here, the n prime here is n into T by Tf. Okay. So, I am going to write this here just to remind all of you that this n prime is n into T by Tf. So, the number of electrons that contribute to the heat capacity, and that tends to n as T goes to Tf, which means at very high temperatures of the order of, I know that Fermi temperature is of the order of 10 to the power 4 Kelvin for most metals. At such high temperatures, it is expected that all the electrons in the system will be contributing to the heat capacity, because all of them will be thermal. You do not have a quantum picture at that at that temperature. You are strongly in the classical limit. So, this then also tells us what is the fraction of electrons close to 0 Kelvin that participate in the heat capacity. Well, you can now say that the fraction of electrons that participate in conduction and hence heat capacity in conduction and hence heat capacity. If they do not conduct, they do not contribute to heat capacity, and heat capacity are basically, you have already written that these are the number of guys participating in conduction, and I am asking you what is the fraction of electrons that participate in conduction or heat capacity. A fraction is basically the guys who are participating over the total number of guys, and this is nothing but T over Tf. And at room temperature, you can think of this number, you can now see that this is a very small fraction. So, this fraction of electrons that participate in heat capacity, okay, at room temperature this fraction is usually 1 upon of the type of the order 1 upon 100, because your room temperature is 300 Kelvin. So, it is like of the order 100, whereas the Fermi temperature is of the order of 10,000. So, I am going to say that this is a fraction of the order of 1%. Okay. So, this is like 1%, 0.01 is like 1%, 100 times this would be 100, 1. So, this is the this now brings us to the final picture that we were chasing from the beginning, that I am now in a position to write down the overall heat capacity of a solid at low temperatures. So, I know that there is a term which comes from the lattice vibrations, and that is proportional to T cube. So, this was the dBi contribution. So, I will say the lattice contribution vibration of ions, that is meant by lattice contribution, and this is basically, I would say, the contribution coming from bosons. The vibrations are quantized in terms of phonons, that are bosons, and we have today seen a contribution coming from the free electrons, and that is linear in temperature. Okay. So, this is due to the free electrons, and these are fermions. So, both bosons and fermions together constitute the heat capacity at low temperatures. And you can see that very low temperatures, the heat capacity would be dominated by only free electrons, because the T cube term which get much smaller. So, it becomes linear at very low temperatures, then become dominated by T cube. Eventually at high temperatures none of these contribute, it becomes the Dulong-Petit 3 Nk at high temperature. So, this is given as a thrice Nk at high temperatures. Okay. Where I am going to assume that high temperature would mean this this T becomes much larger than the Fermi temperature, okay, or even before that. So, this ends the discussion of the free electrons in a metal, and we will discuss the correspondence between the classical statistical mechanics and